Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to this online structural geology course, and today we are at our lecture number 10 where we will study rheology. We have used this term while we were studying strain, where we studied stress, even in the very beginning when we were working with the geometric, kinematic and dynamic models. In dynamic models particularly, we have used this term rheology, but did not explain it properly. So, in this week we will learn about this topic rheology. We will cover it with 3 lectures. In the first lecture we will talk about very basics of rheology. The second lecture will mostly consist of some sort of complex rheology, and the third lecture will talk about what are the parameters, the natural parameters that we commonly experience in earth or rocks do experience in earth, how these parameters influence the rheology. Before we go to this topic, so in this lecture we will mostly cover, we will introduce the subject, so sort of an introduction that what do we mean by the behavior of rocks under stress, which is we will learn later that is the definition of rheology. We will classify the rheology in 3 end members, and these are elastic, viscous and plastic rheology. So, we will sort of discuss all these 3 briefly, and at the same time we will discuss their applications in structural geology together with geodynamics and tectonics. So, before we go to this particular or we take this particular topic rheology to the domain of structural geology, it is very interesting that we as a human being, we use the rheology or applications of rheology every day, or in our actions we actually knowingly or unknowingly use applications of rheology very frequently. So, in the next slide I will have a few questions for you, and I am sure you do these things knowingly, but if you do not do it knowingly, then you can try to answer why do we do that or why it is so. So, we all have used or we still use the ballpoint pens, and there are few ballpoint pens with a spring at the front part of the refill. So, we just press it like this, and then we have a sound tick tock, and then we see that there is a spring if you open the pen. What is the use of the spring? If you ask yourself this question, I am sure you can answer that we use the spring so that after we press, it holds the refill outside, so that your nib of the ballpoint stays outside of the pen, outside the jacket of the pen, and if you press again, then the spring releases and it comes back to its sheltered position inside the pen. It is done so that it does not dry up, or maybe it does not hurt you when you put it in your pocket or somewhere, this pointed end of this refills. So, do we use rheology here? The answer is yes. Next, we all use nowadays tomato ketchup, right? And how many of you shake the tomato ketchup bottle before pouring it to the side of the plate, which is full of snacks? Most of us do, and if you do not do it, you just do once without shaking, and you do second time with shaking the bottle of the tomato ketchup, and you will figure out the difference why shaking makes your life little easier. This is something that athletes or bodybuilders or whoever, they do very frequently. They punch the sandbags, but you don't have to do that. Of course, if you wish, you can do it. But just think that if you have a loose wet sand body and you are sort of pushing your fist within the sand body very, very slowly, you will see that your fist is going in. You can try another way, that you just punch it, and you will feel a pain at your palm if you punch it. So same material, you are going slowly, you don't feel any pain in your palm, on the palm, and it goes inside very smoothly. But if you punch it, you cannot go very far in, and you feel some pain. The question is why? Why do you experience that? Now, this is also something very interesting. You must have seen that soccer players, athletes, they sometimes practice or they run along the beach. They could do it on the side of the roads or on the grounds, but sometimes they do it on the beach. And if you have walked or run along a beach for quite a long time, you feel pain in the night in your calf muscles. Then the similar walk, if you do on the roads or grounds, it doesn't make any difference. If you have not experienced, do that if you get a chance. It's good things to do. And again, the answer is, the question is why? Why do we feel or why it is harder to walk or run on the beach than on roads or grounds? Now, another thing that we use every day, particularly in the morning, the toothpaste. When we squeeze the toothpaste, it comes like a fluid from the tube. But when it comes out and we allow it to rest on the bristles of the toothbrush, then it stays, if you do it perfectly, then it stays like a cylinder over the bristles. It doesn't flow, it doesn't deform, it remains as a cylinder. It does not flow. The question is why? Why it is so? Why it does not flow, but when you squeeze, it is flowing very, very easily. And the final example I would like to give you is that if you have to push a table, a heavy table, and if you have enough muscle, not like me, then you can not move the table instantly after you push. You have to push a little bit, apply some sort of force, and then the table starts moving. Now, when it starts moving, then it becomes easier to move it. Again, the question is why? Now, all these things that we do, that 1, 2, 3, 4, 5, 6 examples that I have given here, is more or less our, not routine all, but few of them we do it every day and routinely. The question is, what is the common in these things? In all these examples, if we can find something common out of it, I tell you these are all applications or examples of rheology. That's why the header of this slide is Everyday Rheology. If I try to see that what is common in all these examples in terms of mechanics, then I'll always find that in all examples there is one or more components of force, stress, one or more components of deformation or strain. So when you push the tip of the ballpoint pen, you apply some force, and then the refill comes out. So you apply a force, the deformation is happening. You shake the tomato bottle, then you squeeze it, applying a force, and then tomato ketchup comes out. You apply a force to the sand body in different ways, and you get different response. The similar way in all examples you can figure out. So based on this idea that all these examples that we see in our daily life, these are nothing but at one side application of force, stress, or in general that we have learned are your dynamic parameters, and on the other side you have your strain, deformation, displacement, rotations and so on, and these are your kinematic parameters. So, we have learnt about stress, we have learnt about strain. Now, this is the point that we should ask in the context of studying mechanics, or in very particular studying structural geology or deformation of rocks, that whether these two terms, stress and strain, which are applicable to our subject very much, are related to each other or not. Okay. And if they are related, then how they are related and what are the controlling parameters in their relationships. And the study of the relationships between stress and strain is the study of rheology. That is not only valid or not only important for our subject, but for most of the subjects, particularly in food industries and so on. So, if I have to define rheology, it's very simple. The second point narrates the definition of rheology: the study of the behavior or flow of materials under deformation is rheology. Now, rheology is derived from a Greek word, rhei, that means flow in Greek. Now, there is a Greek philosopher, Heraclitus. He coined a term or phrase, that's pantharei. So, pantharei in Greek means everything flows, and in his philosophy everything means everything. And we should be happy with this phrase when someone says everything flows, because then we can immediately connect that, wow, do the rocks flow as well? And we'll try to see the answer, and I'll tell you the answer is yes, rocks also do flow. So, this everything flow concept is very interesting, and there are therefore different deformational response to the applied stress, and these responses are functions of their physical properties of the concerned material that you are thinking of or working with, and together with their some sort of external parameters, that means the ambience, the environment you are exposing your material and allowing it to deform. Needless to mention that because it is a relationship between stress and strain, the mathematical or physical understanding of this subject, rheology, is also considered under the umbrella of continuum mechanics. Now, we'll again go back to this very interesting term, pantharei, that means everything flows. And here, therefore, when we talk about flow, the definition of solid and fluid are not really classical as do people define it based on atomic structures of the material. So, there is one set of definitions, what is solid, fluid and gas in terms of solid, liquid and gas in terms of their atomic structures, their interactions and arrangements. But in the study of rheology, as I said that everything flows, so the definition of fluid goes a little funny. It is a material is fluid independently on its atomic structure when it flows under constant stress and of course under certain conditions. Please note, it does not define the time, right. In general, we know that water is a fluid because it takes the shape of a container, right, you fill it up with. So, I have a tea cup and there is tea inside. So, it takes the shape of the cup. If it was a beaker, it would take the shape of a beaker and so on. Now, fluid in rheology is not defined in such a way. So, it is independent of its atomic structure. So, anything that flows under stress is fluid in rheology. Now, it does not talk about time, and let's think of a certain experiment. Say you have a sloping board with uniform friction or no friction if you can make it, and then from one end you have a opening, you have an opening where water can flow, then series of openings with cooking oil, then maybe raw glycerine, wall paint, tomato ketchup, syrup, honey, tar oil, asphalt, and so on. The last one you may ignore. We will see this, but if you want, you can also put some glass. And if you release all these fluids, right, at the same time, you will see water is the fastest to touch the base of this sloping plane. And probably tar oil and asphalt, they are extremely sluggish, and to touch the base it may take few days. Now, we generally classify all of them as fluid, or we consider them as fluid, right. So, the difference between water, cooking oil, raw glycerine, tomato ketchup and asphalt and so on, there is something in their material properties, that they are fluids, but they flow differently under the same conditions. So, gravity is the force working on them, the slope is same, the frictional surface is same. And why do they flow differently? What are the different conditions that can change their flow differently, that can change their flow properties? That what should I do if I have to make the flow faster of, say, tar oil or asphalt for some particular applications? So, if we have these questions in our mind, then we study all these things under the subject rheology. Now, rheology is essentially a very old topic. So, here is I found something very interesting. It's very old text by Lucretius. He was a Roman philosopher and also poet, and he wrote a book on the nature of things, something like that, if I am not remembering correctly, on the nature of things. So, he wrote, for water moves and it made to flow by the slightest force, because is made of little rolling particles. In contrast, honey is more stable, its flow more sluggish and its movements slower, for it has an internal cohesion. The likely reason is that it is formed of particles that are not so smooth nor so fine and round. Now, he wrote this at around, he was there 99 to 55 BC. So, he wrote it long time back, and one of the most famous journals of rheology, that is Journal of Rheology, had one editorial on him, on Lucretius, that one of the pioneers of rheological studies. So, there is something, and you see he is mentioning some sort of, he is finding the difference between water and honey. And people also knew the rheology in the ancient Egypt. So, this is a picture that we see here. So, this is this people found from the tomb of Ramesses III, and what we figured out, that there are a series of paintings. So they're making bread. So it's a bakery, and they call it court bakery of Ramesses III. What these two people were trying to do here, probably this container has dough, so flour and water, and they're doing it with, and they're sort of trying to press it or roll it with their feet, and then this two little rods or whatever are there to check the consistency of this flour, and they know that when by experience, probably they know when the consistency is there, then they send it to the next stage. So, the study of rheology is very old, and we use it for pretty long time. Now, let us slowly move to some similar materials that we commonly see commonly compare with rocks. Talk about the flow of the glass. Now, of course, we all have done it. We have played cricket and soccer, and we've broken glasses. So this is an example. So if you apply some load on the glass, normal glass that we see every day, if you hit it with some piece of stones or your cricket ball or soccer ball, then the glass breaks, it produces fractures, and you can certainly say, hey, it doesn't flow. But the glassware where you make it, when you elevate the glass at high temperature, then it flows like honey. As you can see, this is a jar or whatever, and then he is designing it by rolling with another glass pulp. And interestingly, you can also cut it by a scissor. So here it is extremely fragile, it produces fracture, here it flows like honey, and here you also can cut it. So temperature, at least from this example, we can figure out that it certainly has an influence on the flow of the materials. Let's talk about a relatively closer example to the rocks is the ice, the flow of ice in glaciers. Now, what we see here in this image, this, if I remember, it's from Switzerland, from Grindelwald. We went for a trekking here, and you see this. It looks like that a river is flowing, right? But a river of frozen ice. And the flow of this ice is much slower than the water in a river. You also see that top part is characterized by a lot of fractures, bottom part maybe not, and I tell you it's not. And it flows extremely slowly, but the flow is certainly faster when the temperature is high. That has been recorded. So it doesn't flow like water, it doesn't flow like honey, but it flows like ice should do, but certainly it flows much, much slower rate than water or honey or even tomato ketchup. So now we really have to ask the question that does the rock flow? And because we all live or survive mostly on the upper crust, on the surface of the earth, we don't see every day the rocks are flowing, except some videos of magma flows and things like that from Hawaii and some other places. So our common assumption is that rocks do not flow, and they mostly produce fractures under deformation. And this assumption is perfectly right when you consider them with the ambience of the surface or near surface conditions. But when we go to the mountains, when you go to a hilly terrain or rocky terrain, we see a number of structures which may not be produced by fracturing or cracking. For example, here are some examples I have given: folding, pinch and swell structures, ductile shear zones, and many associated features within the ductile shear zones, the salt domes, magma flow I mentioned. These are the evidences that rocks do flow. We don't see it, most likely because the flow is extremely slow. It's so slow that we cannot see it, but it certainly flows. And the evidences are structures that we see, like folds, pinch and swell, and so on. So based on that, we now are convinced with the fact that the study of rocks under some conditions can be expressed or can be evaluated with this subject rheology that people have been using historically. And if we can do that, then maybe we understand the processes of deformation of rocks in a better and comprehensive way. So when we do that, then there are many subjects or many branches of earth sciences where we apply the rheology. I must say that which was written in the previous slide, that the typical study of rock mechanics is not included under the broader umbrella of rheology, but sometimes it is included, particularly the strength of the rocks at little elevated pressure and temperatures for their engineering and mining applications. Structural geology and tectonics, essentially we use the rheology particularly to understand better the mechanics of folding, ductile shear zones and various tectonic processes at different scales. We consider rheology heavily when we try to understand the processes of solid earth geophysics, like mechanism of earthquakes, physical properties of the interior of the earths and so on, and of course geodynamics that uses the applications of rheology heavily. So, plate tectonics, its driving mechanisms, creep and convection currents in the mantle, upwelling of plumes and what not. So, all these things are being studied under the topic of rheology. Now, we will move to the consideration of the fact that how we can express or how we can study rheology. So, we have stated earlier that mechanical state of a body is defined by mostly dynamic parameters and kinematic parameters. So, kinematic parameters mostly include motion, displacement, velocity, acceleration, distortion, etc., etc. Whether dynamic parameters mostly include different type of forces and their derivatives acting on the rock volume. So, therefore, one has to derive or one has to find a balanced equation to mathematically describe the relationship between the dynamic parameters and kinematic parameters, and these are known as constitutive laws or constitutive equations. And this term constitutive emphasizes the importance of the constitution or composition of the materials. So, if I try to write in general, any rheological equation should have a form like this: dynamic parameters, kinematic parameters should be equated by a constant, right. And if you see that, this is probably coming to the second law of Newton, where force is equated to the acceleration multiplied by mass, right, where acceleration is your kinematic parameter, mass is a constant and force is the one of the dynamic parameters. Now, in earth sciences or in many other subjects including structural geology and so on, the relationships are mostly obtained, the rheological relationship, that is particularly the constant. Finding the constant is the challenge, and these are mostly obtained and conceived by deformation experiments at various conditions in the laboratory. So, they are seen in the form of a stress strain or stress strain rate curves, where strain or strain rate is plotted along horizontal axis and stress is plotted along the vertical axis. And the disposition of the curves, they are different orientations, different way they appear within the framework of the stress strain or stress strain rate plot. One can figure out what are the rheological properties or rheological constants for that particular deformation behavior. So, we will take a break and we will move to the next segment, where we try to classify the rheological part, and that we will cover in the next segment.